This is section 8-4. Most of section 8-4 is meant for graduate students. So read to page 535 and don't bother to go past that. Now, there are other series of approximations. So there's hyperbolic sine, x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, and hyperbolic cosine 1 plus x squared over 2 factorial plus x4 over 4 factorial plus x6 over 6 factorial. And then there's the sine x, x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial. Notice that the hyperbolic sine and the hyperbolic cosine, the hyperbolic sine and the sine function are only different by those minus signs. And the cosine is the same way, 1 minus x squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial. So that's how come the hyperbolic sine and hyperbolic cosine got their names, because this is e to the x plus e to the minus x over 2. And when we look at that, e to the x minus e to the minus x over 2. And when we look at that and say, well, how did I get from here to calling them hyperbolic sine and hyperbolic cosine? That seems kind of silly. Well, once you look at the series approximations, you see, well, it's not as silly as you might think. And then there's the e to the x guy. 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial, etc., etc. And you could put a factorial there and a 1 factorial here and a 0 factorial there and have the same thing. Summation n equals 0 to infinity, x to the n over n factorial. Just in case you need to think about those on the next test, which you might have to do. Okay, we are working problem number 2. So we have x, y double prime plus 5 minus x, y prime minus y is equal to 0. We look at that and we say, well, we have a singular point, so now is the singular point a regular singular point? So we look at the limit x goes to 0 of x, 5 minus x over x, and we see that that's going to be 5. And we look at the limit x goes to 0 of x squared minus 1 over x. We see that goes to 0. Both exist. Therefore, we have a regular singular point. Our P0 is 5 and our Q0 is 0. And we have R minus 1 plus 5R plus 0 equals 0 will tell us what our R's are. So I have R squared plus 4R is equal to 0. I have R plus 4 is equal to 0. Therefore, I can tell you that my R's are going to be, if I have any solutions at all, they're going to be at 0 and minus 4 for my R's. And Frobenius tells us that we will have a solution in one place or the other, maybe both. Okay, so that being the case, we have This is number 2 continued. And I have x summation n equals 0 to infinity, n plus r minus 1, a n x to the n plus r minus 2, plus I have a 5 summation n equals 0 to infinity of n plus r a n x to the n plus r minus 1. I have a minus x summation n equals 0 to infinity n plus r a n x to the n plus r minus 1 minus summation n equals 0 to infinity a n x to the n minus plus r is equal to 0. Okay, so I'm going to bring the things outside the summations into the insides of the summations. Summation n equals 0 to infinity n plus r minus 1 a n x to the n plus r minus 1 plus 5 summation n plus 0, n goes 0 to infinity, n plus r a n x to the n plus r minus 1 minus summation n equals 0 to infinity n plus r a n x to the n plus r minus summation n equals 0 to infinity a n x to the n plus r is equal to 0. Okay, I choose to do a substitution, and I'm going to do a substitution. N is equal to n minus 1, n is equal to n minus 1, and at the end of the substitution I'm going to have summation n is equal to 0 to infinity, and I'm going to have n plus r minus 1 plus, I really did want to put this 5 on the inside. I really did want to do that. So I will do that. Plus 5 n plus r times a n x to the n plus r minus 1. Okay, so those are the first two guys put together, and then I got a minus summation n is equal to 1 to infinity, because when I substitute n for n minus 1, n minus 1 goes there, the 1 goes over there, becomes positive, n plus r minus 1 a n, well, we won't do that yet, n plus r minus 1 minus 1 if I put a minus sign here, there, and I combine those two things, this becomes a plus sign. And a n minus 1 x to the n plus r minus 1 is equal to 0. Okay, seems reasonable. Now I'm going to remove the n is equal to 0 term from that summation, so my indexes are the same. And I'm going to add the 1 to the minus 1 and just have an r plus 1 there. Okay, so that's my plan. And I'm removing the 0, so I have an r. I have an r minus 1. I have a plus 5r. I have a0 x to the n plus r minus 1. No, n is 0, so just r minus 1. The r minus 1 plus summation n equal 1 to infinity. N plus r minus 1 plus 5 n plus r a n minus n plus r a n minus 1 times x to the n plus r minus 1 is equal to 0. Okay, so I deal with the first guy and I say that's fine. When I put a 0 in here, I get 0, so a0 is arbitrary. When I put a 4 in there, I put a minus 4 in there. Minus 4, minus 20, minus another 20, plus 20, I get 0. So a0 is arbitrary, which is always convenient. And I have a recurring formula. Okay, so my recurring formula, a n is equal to n plus r a n minus 1 divided by n plus r n plus r minus 1 plus 5 n plus r. And I look at that a little bit and I say I got an n plus r there, and n plus r there, and n plus r there. And so I got a n is equal to a n minus 1 divided by n plus r plus 4. N plus r plus 4. Okay, so that seems simple enough. We'll copy that, put it on the next page. Okay, so case 1. R is equal to 0. A0 is arbitrary. And recurring formula becomes a n is equal to a n minus 1 divided by n plus 4. Okay, seems good to me. We'll now find some a_n's. N is equal to 1. A1 is going to be a0 divided by 5. N is equal to 2. A2 is going to be a1 divided by 6, which is a0 divided by 5 divided by 6, a0 divided by 30. N is equal to 3. A3 is going to be equal to A2 divided by 7. So that's going to be A0 divided by 30 divided by 7. A0 divided by 210. And when n is equal to 4, I get a4 is equal to a3 divided by 8. which is A0 divided by 210 divided by 8, A0 over 1680. So for case 1, I have y is equal to A0 plus A0 over 5x plus A0 over 30 x squared, A0 over 210 x cubed, A0 over 1680 x to the 4th. And now I'm going to check my work, and we're going to say that y prime A0 over 5 plus A0 over 15x plus A0 over 70 x squared plus A0 over 420 x cubed. We need 2 of them, I think, don't we? Yes, we need 2 of them. So y prime, write it down again, A0 over 5, A0 over 15x, A0 over 70 x squared, A0 over 420 x cubed. And then we need the first derivative, y prime, second derivative, A0 over 15 plus A0 over 35x plus A0 over 140 x squared. Okay, back to the original problem. We need x of those. We need 5 of those. We need minus x of those. And we might need minus of the original guy. Okay, so I look at the A0 term. I have 1 minus 1, and I got 1. Boom, boom, equals 0. I want it to be 0. I look at the x term. I've got 1/5 and minus another 1/5. I have 1/3 and I have 1/15. That becomes 0. I look at the next guy. And I'm looking at the next guy, and I have minus 1/30 plus 5 over 70 plus 1 over 35 plus minus 1 over 15. Put it in my calculator, I get 0. Boom, 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 boom. And I look at the last guy in the line, and I have minus 1 over 270 plus 1 over 180, 108, 108 plus 1 over 180, maybe, plus minus 1 over 90. And I get 0 for him too. This is probably a 40. And he goes away. Boom, 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 boom. Boom. And at that, I have plenty of stuff just tell me that I got the problem right. I'm not done yet. There's still the case 2 part of the problem. So we'll go to case 2. Case 2. R is equal to minus 4. Minus 4. The recurring formula was an is equal to a n minus 1 divided by n plus r plus 4. R is now a minus 4, so I just have a n minus 1 divided by n. And that'll be good for all n greater than or equal to 1. So I look at n is equal to 1. I have a n is equal to a 0 divided by 1. I look at n is equal to 2. I have a n is equal to a 1 divided by 2, also known as a 0 divided by 2. I have n is equal to 3. I have a n is equal to a 2 divided by 3, which is going to be a 0 divided by 3 factorial. N is equal to 4. And I have a 4. Well, I'm not paying much attention to what I'm writing, am I? A lot of talk. 1, 1, 1, 1, 2, 3, 4. A 4 is going to be a 0 over 4 factorial, and a 5 is going to be a 0 over 5 factorial. And with that, we are ready to put our final answer down. So y is going to be a 0 x to the minus 4, because the r is minus 4, so that's going to end up being a minus 4, plus a 1 x to the minus 3, plus that's a 0 x to the minus 3, plus a 0 over 2 x to the minus 2, plus a 0 over 6 x to the minus 1, plus a 0 over 4 factorial, which is 24, plus a 0x over 120, which is 5 factorial. Okay, good enough. Y prime. Now, we need 2 of the y primes, right? Original problem? Yes, 2 of the y primes. So y prime minus 4 a 0 x to the minus 5 minus 3 a 0 x to the minus 4 minus a 0 x to the minus 3 minus a 0 over 6 x to the minus 2. This becomes a 0, and this becomes an a 0 over 120. Y prime, again, I'm going to just write down the same thing all over again and not say much so that I don't interfere with my thinking. Okay, then I'm going to find y double prime. 20 a 0 x to the minus 6 plus 12 a 0 x to the minus 5 plus 3 a 0 x to the minus 4 plus a 0 over 3 x to the minus 3, 0 and 0. Okay, now we need x of him minus x of him, 5 of that one, and minus 1 of that one. And when we get done, we want to have 0. Okay, so we're going to look at the x to the minus 4 term first, and we have x to the minus 4 term, so that'd be this guy, it'd be 4 4, okay. Okay, so I have minus 1. I have plus 4. A minus 1 plus 4. I've got a minus 15. And I have a plus 12. Plus 12. 16 minus 16 is 0. Did I get lucky or what? Now we're going to look at x to the minus 5 term. I have plus 20. I have minus 20. 0. Now I'm going to look at the, okay, I looked at the minus 5, the minus 4. We're going to look at the minus 3 term. So I have a minus 1. Got a minus 5. Got a plus 3. I got another plus 3, which is 0. 1, 2, 3. So those guys go away. Now I'm going to look at the x to the minus 2 term. I've got a minus 1/2. We'll add another plus 0 there. Minus 1/2. I have a 5 over 6. Minus 5 over 6. I've got a plus 1. And I've got a plus 1/3. Okay, well, so I got 5 over 6, 3 more over 6. I have 8 over 6. I got 8 and 2 makes 8, so this is 0. So the x to the minus 2 term goes away. And I'm going to look at the x to the 1 term. X to the 1 term. Okay, so we'll come back and put another plus 0 there. X to the 1 term. So I got minus 1/6, and I've got plus 1/6. So that's going to be 0. Then I'm going to look at the 0th term. 0th term. So there's minus 1/24 and plus 1/24. So it goes away. And then I look at the x term, and I see that the x term goes away, but does it? I got minus and minus. So for some reason that term doesn't go away. That's probably because I don't have enough terms. So I checked. Everything's good with the x is equal to minus 4 term. Okay. And also, if you'd look in the back of the book, you'll notice that the back of the book has the wrong answer. Isn't that clever of them to put that in? Okay, now we're going to look at number 4, section 8-4, number 4. I have 5x y double prime 30 plus 3x y prime plus 3y is equal to 0. I look at that and I say, well, I do have a singular point at x is equal to 0 if I write the equation right. So I'm going to have to look and see if I have a regular singular point or not. So limit x goes to 0, x 30 plus 3x divided by 5x, and I see that that's going to be 6. And the limit as x goes to 0, x squared, 3 over 5x, which is 0, both exist. Therefore, I have a regular singular point. And my P0 is 6, and my Q0 is 0, and R minus 1 plus 6R plus 0 is equal to 0 will tell me what my R's are. So I've got R squared plus 5R is equal to 0. This sort of implies that my R's are going to be minus 5 and 0. Boy, that's a lousy bracket. Don't know if I want to correct it or not. Maybe the computer will do it for me. Well, that's a little better. Okay. So now we look at the problem 5x. So I'm going to have 5x summation n 0 to infinity. N plus r, n plus r minus 1, a n x to the n plus r minus 2, plus 30 plus 3x, 30 plus 3x, summation n equals 0 to infinity, n plus r, a n, x to the n plus r minus 1, plus 3, summation n equals 0 to infinity, a n x to the n plus r is equal to 0. Okay, now we're going to start rewriting that. So I'm going to have summation n equals 0 to infinity, 5 n plus r plus minus 1 a n x to the n plus r minus 1 plus summation n equals 0 to infinity, 30 n plus r a n x to the n plus r minus 1 plus summation n equals 0 to infinity, working on that guy now, 3 n plus r a n x to the n plus r plus summation n equals 0 to infinity, 3 a n x to the n plus r. Okay, we're going to do a substitution. N is equal to n minus 1 into both of these guys. N is equal to n minus 1. That way I have n plus r minus 1 and plus r minus 1 up there. Okay, I'm going to do that, and I end up with summation n equals 0 to infinity, 5 n plus r minus 1 plus 30 n plus r a n x to the n plus r minus 1. Now I'm going to do my substitution plus summation n equals 1 to infinity, 3 n plus r minus 1 plus 3 a n plus n minus 1 n minus 1 x to the n plus r minus 1 is equal to 0. Okay, so now I'm going to remove n is equal to 0 from the first summation guy. Okay, so I'm going to do that. I'm going to have summation. No, I'm not. I'm going to remove it first. Alright, so n is equal to 0. I got 5 r minus 1 plus 30 r times a0 x to the r minus 1 plus summation, and I'm going to put everything in the same summation. That's an n in case anybody was wondering. I have 5 n plus r minus 1 plus 30 n plus r a to the n plus 3 n plus r minus 1 plus 3 a to the n minus 1 x to the n plus r minus 1 is equal to 0. Okay, look for any funny business up here. I have r squared minus 5r, so 5 and blah 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 blah. So 5 and 0 are my minus 5 and 0 are my, so there's nothing funny going on up there, so that's good. Always good to check. Okay, I have a recurring formula. Recurring formula. an is equal to 3 n plus r minus 1 plus 3 divided by that guy. 5 n plus r minus 1 plus 30 n plus r. Okay, so I'll do some algebra. Multiply through by 3. I have 3 n plus r plus 3 minus 3. That goes away. On the bottom I have 5 n plus r minus 1, 30 n plus r. And I see that I have the n plus r in all my terms, so I can get rid of it. So I end up with 3 divided by 5 n plus r plus 25. 3 n plus r plus 25. And there's a couple problems here. So let's move up a little bit. When that went to the other side of the equation, it gave me a minus sign right there. And I'm missing my a n minus 1 sitting there. Okay, so I got a minus sign, and I have an a n minus 1 sitting there, a minus sign, and an a n minus 1 sitting there. Okay, so now I'm happy about that. I'm not happy that I did that, but I'm happy about that. And we'll go with case 1. I'm going to look at this guy for a moment. He's a little big. Okay, so what we're going to do is copy my formula and move to a new page. So we're doing number 4 in 8-5. And I got a recurring formula. See if I can get rid of those marks. Okay. It's my recurring formula. And case 1, r is equal to 0. Okay, so recurring formula becomes a n is equal to minus 3 an minus 1 divided by 5r plus 25. 5n plus 25. R is 0. 5n plus 25 for all n greater than or equal to 1. So at n is equal to 1, I've got an a1 is equal to minus 3a0 divided by 30, also known as minus a0 over 10. Okay. At n is equal to 2, I have a2 is equal to minus 3a1 divided by 35, which is minus 3a0 over plus 3a0 over 350. Okay, and at n is equal to 3, I have a3 minus 3a2 divided by 15, that'd be 40. And so I got minus 3 over 40 times 3 over 350 a0, which becomes minus 9 over 14,000 a0. Well, those are getting pretty big pretty quick, so I guess we'll check to see if that answer comes short or not. So y a0 plus minus a0 over 10x plus 3a0 over 350 x squared minus 9 over 14,000 a0 x cubed. Y prime, and we need two y primes. All right, so y prime minus a0 over 10 plus 3a0 divided by what? 175 x minus, well, it probably doesn't, 27 over 14,000 a0 x squared. Okay, we need two of them. Okay, so everything's good. And then we need a y double prime, 3 over 175 a0 minus 27. So 7. So that'd be, the 2 goes over here. That makes it 7,000. But I can divide 7. No, I can't. Forget that. Okay, so minus 227 over 7,000 a0x. And we want 5x of him, 3x of him, 30 of that guy, and the y guy, we want 3 of the y guy. 3. And when we get done, we want to have zeros across the board. Okay, so I'm looking at the a0 term. I have 3, and I have minus 3. Boom, boom, gone. I look at the x term, and I have minus 3 over 10. I have 300 over 175. I have minus 3 over 10, and I got minus 15 over 175, and that becomes 0. Boom, 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 boom. The x squared term, boom, 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 becomes 0. You can check it if you'd like, but it does. And so the solution for case 1 is correct. So isn't that lovely? So now we got to do a case 2 solution. So we're doing problem 6, I think, and we're in section 8-4. And I think if I just do that, I get my recurring formula back, an. And now we're going to do case 2. N is equal to minus 5. Alright, so an is equal to minus 3, an minus 1 divided by, not n, r is equal to minus 5. 5, n minus 5 plus 25, and that becomes the awesome 3an minus 1 over 5n. For all n greater than or equal to 1. Okay, so I got n is equal to 1. Oh, a0. a0 is arbitrary. N is equal to 1. a1 is equal to, there's a minus sign sitting here, minus 3a0 over 5. N is equal to 2. a2 is equal to minus 3 divided by 10 a1. So that's going to be 9 over 50 a0. N is equal to 3. a3 is equal to minus 3 over 15 a2. So minus 3 over 15, so that'd be a 5 on the bottom, so that'd be minus 9 over 250 a0. And we'll do one more. N is equal to 4. a4 is equal to minus 3 over 20 a3. Okay, so that's going to be 27 over 5,000 a0. Okay, and we go and say final answer. Y is equal to a0 x to the minus 5 because r is minus 5. Minus 3 over 5 a0 x to the minus 4 plus 9 over 50 x to the minus 3, a0 x to the minus 3, minus 9 over 250, a0 x to the minus 2, plus 27 over 5,000, a0 x to the minus 1. And we'll do a check with back of book, and we see that that one's correct. And we'll move on to problem number 6. This is really problem number 4 that I'm working on, not number 6. Okay, I was working on problem number 4. Everybody knew that but me, probably. Okay, now we're working on, we're in section 8-5. No, we're not. 8-4. And we're doing number 6. I have 2x, y double prime, minus 6 plus 2x, y prime plus y is equal to 0. I look at it and I say, well, if I rearrange it the way I should, I'm going to have a singular point. So I'm going to have to figure out whether or not I have a regular singular point. So limit x goes to 0, x 6 plus 2x divided by 2x is going to be 6. Now the x goes away. I have a minus sign sitting up here that I had left out. It's going to be minus 3. Yeah, that's better. Okay. And then I got limit x goes to 0 of x squared 1 divided by 2x, which is 0. So they both exist. Oh, I misspelled both pretty bad. And therefore I'm at a regular singular point. X is equal to 0. My P0 is minus 3. My Q0 is 0. I look at R minus 1 minus 3R plus 0 is equal to 0. And I end up with R squared minus 4R is equal to 0. R's are going to be 0 and 4. Alright, so that's pretty good. Well, now I'll solve the problem. 2x summation n equals 0 to infinity. N plus r minus 1 an x to the n plus r minus 2 plus minus 6 plus 2x summation n equals 0 to infinity n plus r an x to the n plus r minus 1 plus summation n equals 0 to infinity an x to the n plus r is equal to 0. Okay, so we got the problem written down. Now we'll try to solve it. Bring the 2x inside. Summation n is equal to 0 to infinity. 2 n plus r minus 1. Okay, when I bring the 6 in, I'm going to have the same n plus r minus 1 on this guy. So I'm going to bring him in too. So I'm going to say plus 6 n plus r bracket a n x to the n plus r minus 1. Okay, except for one minor insignificant problem, and that is I have a minus sign sitting there, so I better use it. Okay, so now I've got plus summation n equals 0 to infinity. I'm going to bring in the 2x, 2 n plus r an. I'm going to bring in this an as well, so we're going to not put the an down yet. I'll put a bracket plus 1 an x to the n plus r is equal to 0. Okay, so maybe I did that right, and maybe I didn't. And of course I didn't. The minus sign that's sitting here that I didn't put there, I also didn't put here. So I have to put it there, I have to put it outside. We'll put it outside. Now we can't put it outside because the other guy is plus. Okay, so we'll keep the plus sign there, we'll put the minus sign here. So that minus sign has to be there. Okay, so now I've done that, I'm going to do a substitution of n is equal to n minus 1 in the bottom guy. Okay. And at the same time, I'm going to remove, this is dangerous, n is equal to 0 from the top guy. Because if I do this wrong, it's going to be hard to find the error. Okay, so I'm going to have n equals 0. So I have 2r, n plus r, n is 0. 2r, r minus 1, minus 6r, a 0, plus summation n equals 1 to infinity, double bracket, 2 n plus r, n plus r minus 1, minus 6 n plus r, a n, plus bracket, minus, we don't have enough room, so we'll continue down here. So I got a plus sign, bracket, minus 2 n plus r minus 1 plus 1 a n minus 1 bracket x to the n plus r minus 1 is equal to 0. Okay, now I look in this guy, I'll look at him first to see if there's something funny going on. So 2 r squared minus r minus 2r. Oh, we'll try it again. I have 2r squared minus 8r a0 has to be 0. When I put in a 0, this is 0, so a0 is arbitrary. When I put in a minus 4, is the other guy minus 4 or plus 4? When I put in a 3, put in a minus 3. No, 4. 4 is correct. So I put in a 4, and 4 squared times 2 or 4 times 8 is the same number. Okay, so there's nothing funny going on, and we can write down our recurring formula is going to be an is going to equal minus 2 n plus r minus 1 plus 1 a n minus 1 divided by 2 n plus r minus 1 minus 6 n plus r. Okay, so that's going to be my recurring formula. And now we're going to have to do some algebra with that so that it's a little less messy. I'm going to minus 2, okay, so that looks all right. Okay, what am I going to do with that? Okay, so a n is going to be, the minus sign comes in, I have 2 n plus r. Then I have a minus 2 and a plus 1 and a minus 1 for a minus 3. And then on the bottom I have 2n plus r, n plus r minus 1, minus 6, n plus r. And I can't do much with that. Alright, so that is going to be my recurring formula. I look over here and I see I'm filling up the page. So I'm going to take my recurring formula to the next page and do case 1. Copy. Okay, so case 1, r is equal to 0. Okay, when r is equal to 0, recurring formula becomes an is equal to 2n minus 3 divided by 2n, n minus 1, minus 6, n. Okay, minus 6n. an becomes 2n minus 3. I've got an n squared, I got a minus 2n, I got a minus 6n, I've got a 2n squared minus 4 for all n greater than or equal to 1. Okay, so a0 is arbitrary. Okay, so we're there. We're going to look at n is equal to 1. a1 is equal to minus 1 divided by 2 times minus 3 a0. This is a n minus 1, a n minus 1, a n minus 1. Okay, which is a0 over 6. N is equal to 2, and something bad happens. Bad. I'm dividing by 0. Now, as soon as I get myself dividing by 0, that implies something. That implies there's no solution for r is equal to 0. So that's a good thing. That cuts down my work. So now I'm looking for the r is equal to 4 solution. Number 6, section 8-4, case 2. R is equal to 4. And I think we can edit, paste our, we'll go to there, edit, paste our, this guy in. And we know we made a mistake, so we'll correct it. And now we have n is equal to 4. Power is equal to 4. Okay, an is equal to 2 n plus 4 minus 3 a n minus 1, 2 n plus 4 n plus 3 minus 6 n plus 4. Isn't that lovely? And on the top I have 2n minus plus 5. 2n plus 5, a n minus 1. And on the bottom I have 2n squared, 2n squared plus 8n. Okay, and that's going to be my recurring formula for all n greater than or equal to 1. Okay, so I'm going to look at n is equal to 1. A0 is arbitrary, so A1 is going to be 7 divided by 10 A0. And n is equal to 2, and A2 is going to be 9 divided by 4 times 2 is 8. 8 plus another 16, 24 times A1, which is going to be 21 over 80 A0. And n is equal to 3. A3 is going to be 3. That's 6. That's 6 and 5 is 11. 11 over 42 A2, which is 11 over 42 times 21 over 80 A0, which becomes 11 over 160 A0, and n is equal to 4. A4 is equal to 8 plus 5, 13. 4 squared is 16 times 2 times 64. 64 A3, which is 13 over 64. A3 times, not A3, times 11 over 160 A0, which becomes 143 over 10,204. You know you're far enough when you get numbers that big. Over 0. Okay? And r is equal to 4. So my final answer looks like y is equal to A0x to the 4th plus A0 over 10 x to the 5th plus 21 over 80 x to the 6th plus 11 over 160 x to the 7th plus 143 over 10 to 40 x to the 8th. Isn't that lovely? And we'll leave that for you guys to check, so class can check. But I have it on very good authority that it is correct. So if you don't get it to check, do it again until you do. Okay, that ends section 8-4. Remember that in section 8-4 we are not going to read anything past the first example. Okay.